Okay, so let's go ahead and do another distance problem. This time where you just change some things up, but the dynamics are the same. So this time we're going to let P be a point. Again, we'll call it x comma y. That's actually on the graph of y equals x squared minus 3. So it's not a line, it's a parabola. So drawing a picture, right, we know that this is a parabola that's going to be shifted down 3. So 1, 2, 3. So we're looking at that graph right there. So here's y equals x squared minus 3. And we're talking about any data point, right? There's millions of them, but any data point, P, right, along that edge. And we want to find an expression for the distance from any point on that graph to the point 0, 2. So in black, here's the point 0, 2. Okay, and so what we want to basically do is find the distance between that point and any other point on that graph. So again, as you can see from last problem, anytime I change my position on this function, I change my distance to that point. So again, the distance is in fact a function itself, which means this is well defined, right? We should be able to find a function as a function of x. So again, our distance formula between any 2 points anywhere in the plane is given by this formula: x2 minus x1 squared, y2 minus y1 squared. And in this case, our first point is that fixed point 0, 2, and then our x2 and our y2 is any data point that's on this curve. So plugging this into the formula, we get d equals x minus 0 squared plus a y minus 2 squared. And that basically is d equals, let me come over here, the square root of x squared y minus 2 squared. So there's what our function is at the moment in time and that we're working with. Alright, so again, you notice that this is in terms of 3 variables. I would need to know both the x and the y coordinate to find the distance. But we have a constraint equation, right? Y has to be equal to x squared minus 3. So come and substitute it. We now get a function of x. So d of x, if we clean this up, is x squared. I think what we end up with in here is x squared minus 5. We're going to square that, I forgot to square it, and then take the square root. So again, obviously this is not a quadratic function, right? But we're still going to be able to analyze it and do things with it. So here's the function. You give me an x coordinate, and I'll basically tell you what the distance is away from the point 0, 2. So let's use it to find the distance when x is equal to 1, right? So imagine 1 right there. So when x is equal to 1, our point is somewhere down here on the graph, so we're looking for that distance. So how far away are we? Well, we just plug it in. So d of 1 becomes 1 squared plus 1 squared minus 5, and then that quantity squared. So it looks like we get 1. 1 take away negative 5 is negative 4 squared, square root. We get 1 plus 16. So it looks like that distance is the square root of 17. And whatever that is, it's roughly about 4 point something, because the square root of 16 is 4 and 17 is higher. So about 4 point something. Okay, so that's how far the distance is if x is equal to 1. As a matter of fact, we even find, I think we're negative 2 there. So my graph, so at the point 1, negative 2, that point is sitting the square root of 17 away from the data point 0, 2. So that's at x equals to 1, is there a value of x that gives us a minimum distance? And I think just visually we can see that there are, right? So it's kind of long. So maybe about over here and over there, right? So there's actually 2 values, positively and negatively, where we reach kind of a smallest data point. We get a little long again, come back to short, and get a little long again. So we can visually see that there is some locations where there will be some shortest distance. But let's go ahead and turn to our graphing calculator to graph this function and then find them out explicitly. So again, we'll reach for our graphing calculator and make sure it's on. We'll put in our function, so it is the square root. We have an x squared, and then we're going to add parentheses x squared minus 5, close parentheses, and then that piece is squared. So there's basically the function. I think we're fine on the standard viewing rectangle, and there's basically what the distance function looks like. So we can see that there actually are two minimums to its left and to its right. So we basically have to find those. And so picture-wise, again, if this was homework, you would tell me what you entered, right, which is all that. And then the picture on the standard viewing rectangle looks like this. And we're interested in those two data points right there. And so one of them and two of them, let's go ahead and use the calculator. I can also we probably only have to do the work once because we are symmetric. Notice that the graph over on this side is the same as on this side. So if we basically find one of these minimum points, by default we found its corresponding negative. So let's just use that even function to help us pay off. So we're going to calculate a minimum. How about I calculate this minimum over here? So again, I need my cursor to be just to the left of that minimum value, press enter. I need my cursor to be to the right of that minimum value, press enter. And then we're going to come in here and settle in, press enter, and it looks like we get 2.121, right? Which means that this is negative 2.121 because of the symmetry. We also have the y-coordinate if we were interested in that, right? The y-coordinate is 2.179. y.2.179. So if we needed that, although we're just finding the x values that it is. So that means that on our graph, if we went out 1, 2, and a little bit more, right, those would be the points where the distance is at a minimum with regard to the point 0.02, and that looks pretty messy. Hopefully you guys can follow along there. All right, and so there again, you can kind of see that rhythm. So we're going to have our distance formula, and we're going to plug in our data point that's on the constraint. We're going to use the constraint to replace the y, giving us a function of x. And then once we have that function of x, we can analyze it for any value of x to find a distance, and then we can even analyze it to find, in this case, the smallest distance that we have. And there is your classic distance to point problem throughout section 3.6. They all pretty much have that same rhythm. The only thing that can change on you really is the constraint. Maybe the constraint's linear like the last problem up here. Maybe it's quadratic. Heck, we can even get cubic, right? And and still find the distance between a cubic graph. The rhythm's the same. Start with your distance formula, plug in the data point, and then replace the y with the constraint. And that basically gives you what you need to do all your analysis, and then it's basically graphing calculator work after that. So practice, practice, practice. I think there's quite a few homework problems where you'll work through that. Post them online. Let's get a feel for everybody's learning process, and we'll go from there. Talk to you guys. We'll be changing gears and talking about area in a moment.